We have three states of matter that we're tracking: solid, liquid, and gas. And our matter, our molecules that are compounds, are samples that are just one type of molecule. That's what we're going to be thinking about here. Um, they can transition between these different phases of matter. If energy is put into the system, into the matter, if it has more and more energy, maybe it's absorbing that through heat. Then what we're able to see is that the solid will get more and more and more motion until it's able to be a liquid and kind of tumble all over each other. And if we keep applying heat into the system, which is applying energy and giving energy to it, then the liquid will get more and more energy, which means more and more motion until those molecules are no longer in the liquid phase, but in the gas phase. So we will be increasing the amount of kinetic energy a sample has by heating it. So heat's the way we're going to transfer that energy. And if we want to reduce the amount of kinetic energy that a sample has, we're going to cool it down, like put it in a fridge or a freezer. Is that will remove or reduce the heat, which will remove energy from the system and slow things down. And so then we would see a gas condense or turn into a liquid and then turn into a solid. And so these changes, phase changes that occur, have names to them. And so let's walk through them. Let's start with a solid. Um, so here we're looking at solid ice right here. So we're thinking about water. And if we are heating things up, then that liquid or that solid ice will melt and it will melt into liquid water. And so hopefully at least this is familiar, right? Or some of these terms. Once we have liquid water, if we continue to heat it up and we keep heating and we keep heating, think about putting it on the stove, we will see it evaporate. And there's a few names for this process of going from a liquid to a gas. One of them is evaporation, one is vaporization, or boiling. And all three of these terms are meaning the same thing, which is the phase transition from a liquid to a gas. All right. So the other way this could happen is with, I guess, heat, is we could go straight from a solid to a gas. We could input heat or we could play with pressure and we would see some of that solid just skip the liquid phase altogether and become a gas. And if you've ever put ice tray with water in it, put it in your freezer, you make ice. Great. So you've got some ice sitting there. If you just leave it there for a really long time, like let's say you put it in there in the winter, you're not really drinking icy cold beverages because it's cold out, you're having tea instead. And let's say you come back 3 months later and you go to get some ice for something. You look at it and the ice has gotten really small, right? You're like, I'm sure I filled that ice tray up to the top with water, but my ice cube holders are just about half full. Well, a lot of that water really just transitioned from that solid ice phase to the gas phase through a process called sublimation, where it transitions without going through the liquid phase of melting. Um, so now let's think about this the other way. Let's get a different color. So let's say we start with a gas. If we have a gas, so we've got steam, water, and it transitions to a liquid, we're going to be removing heat. It's going to condense, right? So for a gas to go into a liquid, heat needs to be removed. This happens outside in the morning when it starts, when it's really cool. In the early morning, we get the water vapor in the air will condense onto leaves as droplets of water or dew. And so that process is condensation. The same thing happens in your car too. When there's gas air around and it condenses on something that's colder, right? So this transition is condensation. Now you have liquid water, and as it goes to form a solid, you'll call this freezing, which is luckily an easy one to remember. Um, Now, if you were to go from the the gas just to the solid phase, with skipping the liquid phase, we would call this deposition. And we do this, it's an interesting way to like get a very thin film of element or a molecule on usually like a piece of plastic. Um, and maybe you're doing this because you're building an electrode, right? And so you can use deposition to take a gas of something you're interested in and put it onto a solid and get like a nice uniform layer of it, which is pretty cool. But our most common ones are freezing and melting, and evaporation or vaporization and condensation. So these are the ones that we'll look at the most here. I like this circular diagram for our phase changes, but we typically actually think about them as a diagram that's a graph. So I'm going to go through the phase change diagram for heating and then for cooling. And these are going to use axes of temperature. And so here's, temperature, and then heat added. So heat added would be something like I have put something on a stove, right? So this temperature is reading the temperature of the matter. So it's increasing as we go up our scale. Heat added is us applying energy into the system. So it's kind of like putting something on a stove and turning it on. So as we put more and more heat in, which means like as we leave it on the stove, we'll have a solid that is down here at low temperatures. We will then hit a certain point where our solid starts to melt. So you would see the ice cubes start to turn into a puddle of water, and you'll still have a chunk of ice and a puddle of water. So that phase transition is called melting, and that's right here. So notice that the temperature stays the same. It will be constant as the phase transition takes place. We're putting more energy into the system, but all that energy is now going to each molecule or atom having more motion to start moving around as a liquid rather than stay in one spot as a solid. And so during that process, the temperature of the matter doesn't increase at all. And so that's why when you have like a glass of ice water, the entire time there's ice in the water, it stays at the same temperature. It's 0 degrees Celsius for water. And this is its freezing point or its melting point. It's called both things. So this temperature right here is the melting point. Or you might see it called the freezing point. So for water, that is 0 degrees Celsius. And that temperature where that occurs is unique to water, and it is a physical property of the water, the temperature with which that phase transition takes place. And so for a different molecule like ethanol, it's going to be at a different temperature that it freezes or melts, which is why you can put a bottle of vodka in your freezer and it doesn't freeze solid. And that's because the ethanol has a freezing point that is a lower temperature than the water has. And when you mix them together, it lowers that point where it forms a solid. All right, so we keep adding more heat and more heat and more heat, and we have a liquid. And now the temperature of the liquid, since there's no solid around, is going to start increasing and increasing and increasing as we put more heat in, as we leave it on the stove, until it hits a new point, and that's going to be its vaporization point, or its evaporation point, or its boiling point. And so here, for water, that is going to be 100 degrees Celsius. And so this right here is going to be its boiling point. You could also call it its evaporation point or its vaporization point. But boiling point is the one that you see the most, most commonly. And that's the temperature where our liquid becomes a gas. And for a period of time, you'll have both phases present and the temperature will stay constant. And so for water, that's 100 degrees Celsius, which means that we cook things in boiling water, not just because the temperature's high, but it's consistently high. If water's boiling at sea level, it's going to be the same temperature the entire time there's a rolling boil, where we have both gas, water, gas, steam, that's the bubbles going up and then, releasing into the rest of the atmosphere. And the water that's hot to the point that it's starting to convert from a liquid to a gas. And then once all of the liquid water is converted into a gas, then that gas temperature, if you keep putting heat into the system, will continue to increase and increase and increase, which is why you will get burned much more by steam than you would by boiling water, right? If you've gotten those steam burns, they hurt. So those are our different physical properties, the boiling point and the melting point. And what we call this diagram is a heating curve. We can see also a cooling curve. So here's one right here. And in this case, the real difference is that we are, our x-axis here is showing heat removed. We're still looking at temperature increasing on our y-axis. And so we're going to start with a gas at a high temperature and then see what happens as we remove heat. And we see that expect the temperature to go down as that heat is removed. You can remove heat from a system by putting it in someplace colder, because the heat will spontaneously kind of transfer to the surroundings that are colder. So like putting it in a fridge or in a freezer would do the trick. So here we start with a gas, and as the temperature decreases, it'll finally hit a point, and that's going to be its boiling point still, or the condensation point, but we usually call it boiling point, because it's really just the temperature where the phase transition occurs, whether it's boiling or condensing. The transition between a gas and a liquid will contain both gas and liquid of that matter, and it will happen at the same temperature, whether you're heating it or cooling it. And so that boiling point is still going to be 100 degrees Celsius for water. And so that's when the gas at the higher temperature will start to condense. And so then once that condensation takes place, it'll be 100 degrees the whole time until it hits the point where everything has been converted into a liquid. And then the temperature, as you continue to remove heat, will drop and drop and drop on that liquid until it hits its freezing point, which is the same as its melting point. Which is 0 degrees Celsius for water. And then as that liquid converts into a solid, and for a while it'll have both of those phases present, the temperature will remain constant. It'll be 0 degrees Celsius. And then once everything is a solid, then the temperature will start decreasing more and more and more. And so this is called a cooling curve. As well, that we kind of represent this graphically.